So today we're going to talk about Hoffman's theorem, which has not been published yet, and I just made it up yesterday, and I want you to look over it and see what's wrong with it, and if it needs tweaks or if it's good. And it's derived off of the divergence theorem, and the divergence theorem states if you have a vector field f of x, y, and it is, let's say, x I hat plus y j hat, then that means the flux across the border of a two-dimensional surface inside of the vector field that is parallel to the unit normal vector, or that is, yes, is equal to the surface integral of the divergence of f dot dA. So this is basically saying that if you the flux across the border of a two-dimensional surface in a two-dimensional vector field is equal to the surface integral of the divergence of f. So, and it's over sigma, which is the surface of this two-dimensional surface. And it's bounded at a point x and a point y. So let's say, and dA is actually dx, dy. I don't want to write that, so most people just write it dA. So you have this evaluated at 3 and negative 3, and then this evaluated at 2 and negative 1. Take the antiderivative of 2 with respect to x, and we get 2x, and we substitute 3 and negative 3, or we evaluate it at 3 and negative 3. We get 6x, because 3 times 2 is 6, and 6 times x is 6x, minus negative 3 times 2 is negative 6. So minus negative 6x is the same thing as plus 6x, and that's equal to 12x. So the integral evaluated negative 1 to 2 of 12x dy, and that's equal to 12xy evaluated 2 to negative 1, and that's 24x. 2 times 12 is 24. xy plus 12x, because negative 1 times 12 is negative 12, and minus negative 12 is plus 12xy. And that's going to be equal to 13xy. 36xy, sorry. And so that's an example of the divergence theorem. But I derived the divergence theorem, and it has to do with electromagnetism, of course. And it states that if you have an electric vector field, so it's like, let's say it's like this. If it's like this, you could probably guess what is at the vortex of this vector field at point 0, 0 in this vector field. If the vector field is fxy equals xi hat plus yj hat, and by Gauss's law, it's a photon, of course. Because photons produce an electric field that looks like this. Shoots out in all directions. It has a positive divergence. And this, an electron, however, has a vector field like this. And it had negative divergence. So Gauss made up a rule, and it says that the divergence of the electric field is equal to Q enclosed. Or Q, really. And it states that if you have a cube, or any shape, any closed shape, then the flux across the border of it would be the divergence of the electric field, which is equal to the charge inside of it. So using this is equal to Q, I derived it, and before it said this. Surface integral. Now it says this. Which is equal to Q. And the reason this term is equal to this term is because since you have a vector field and a charge is not shown right here, when the vector field is equal to, or E really, is equal to x I hat plus y j hat, it's because that there's no charge, so you're assuming there must be a positive charge right there. Actually, you know there's a positive charge right there, because there couldn't be an electron there, or there would be negative divergence of the electric field. So there's no reason to take the surface integral with respect to dA of it, because it's going to give you the same answer. It's like multiplying by 1. And so it's E to N dL is equal to the surface integral and this of, where did I put that? Equals equal to Q. So if we wrote this, and I said that the electric charge density was equal to, or let's say A, let's just say pho, is equal to Q over A. And I did that pho times A is equal to Q. So this is equal to E dot N dL is equal to, so it's dependent on the electric charge density in the area now. So if we had a cylindrical loop like before, then this term, or really any loop, would be equal to the electromotive force.
Here, you can eat outside with Daddy, okay?
Shh. So the electromotive force is equal to the charge density times A. I'm going to put C instead of epsilon, you know. But since there's what's the formula for electromotive force? I forgot.
I don't know.
Whatever. So that means the electromotive force is equal to Q. Based on the divergence theorem. The Q enclosed, actually. So what if we have a cylindrical loop? Wait a minute. Oh, yeah, if we have a cylindrical loop, then the electric field coming out of that direction with Q enclosed, with the charge enclosed, is equal to, the two are equal. The charge enclosed and the electromotive and the electricity going on in that direction. Done.